Structural Analysis 2, Chapter 9, Force Method. Let's solve Determinate Beam example with force method. So in this example, if we want to calculate the reactions at supports with this kind of loading, we can easily see our structure is 1 degree indeterminate. And for example, like we can consider RB like redundant. We just dissect our structure to two parts. A cantilever beam with the effect of the real load, like a distributed load all over the span, plus a cantilever without any load, but just the effect of the reaction at B. So then if we just observe the downward motion delta B W downward from our cantilever determinate structure, and also the other one delta RB, which is upward, and observe the real structure and its support B, we can easily see there is no delta B. So delta B is equal to 0. It just says delta B W minus delta B R should be 0. Then delta BW, let's see how we can approach it. And the only unknown in this equation is RB. And you can calculate one reaction, redundant reaction, and with the help of equilibrium equation, you can get all the other force and moment, like RA and like MA. Let's see how we can approach the problem. So if we know the deflection format of cantilever beam distributed load, we can see a drop down, a climb down of delta B is equal to C. If we calculate the reaction at A is WL, that's our V, and area under is the amount of M of EI. And you know at the Vn we don't have any moment, so we don't have any moment here. And at the other end we do have a moment, which is the area under V. So that's W times L over 2, that's WL squared over 2, and because that's M over 5 for calculation, at the same time we do know delta is tangential moment of with respect to a horizontal reference, which is A here. So it means if we draw a horizontal line and this is our tangent, can easily see delta B is equal to TB with respect to A. And due to second air moment area method, that's area under nothing but M over EI from A to B times X, and X is centroid. So if this is constant for loading, this is 1 degree linear, 1 degree, and arc degree, and this is a second degree curve. And this is, if this is second degree, this is one force, and the other part, which is TBA, is area under moment times X, which is a 3/4 of length from centroid to B. So if you do the math, it just gives you 1/3 of 1/3. If it's second degree, area is 1 over n plus 1, and that's 1/3 of W L squared over 2 times then L, which is length, then times X, which is a 3/4 of L, and then the centroid is 1 over n plus 2. So that makes us a delta B, the distributed load only over the cantilever beam is WL to the force over 8 EI. So we get the first part. Let's jump to the other part, and if we just draw the second part, you can easily see delta R is equal to RBL cubed by 3. You can calculate it with a drawing method, moment area method, integration method, with cantilever, with Castigliano's method, or you can just read it out from the chart. So as soon as you have delta B or RB, if you equalize two equation from both parts, so this is first equation, first beam, this is second beam, or we can call it this is the second one, this is the third, doesn't matter. Then the real structure, we do know delta is equal to 0, and the only unknown here is RB. RB is 3/4, then 3 over 8 times W. RB, the main structure, is 3/8 over W. Definitely RA is 5/8 of W, and you can also easily calculate MA. There is another method for this calculation, so we call it solution 2. You can consider, you can again dissect our in the 1-degree indeterminate structure, but this time a 2 just remove, consider the moment at here like a redundant, so we can consider moment at A. So as soon as you release moment from the fixed support, it just turns to two simple support being one pin and one a roller. So as soon as you have that, you can add it with a simple support being with no loading but a down a part of the structure, support A. So then we have theta here, have a theta. So as soon as you have that one, you can calculate theta at A, which is A identical to theta at B symmetry, and that's nothing but WL cubed over 24 EI. And the reason for you can calculate this part from a different method, and theta A is if you have apply a moment on a two simple support, the near end theta is ml over far and ml over 6 ei, which is a bit half of that is smaller definitely. So if these two moments are canceling out each other, because in the real structure it was a fixed no theta no delta, so the beginning there is no theta is equal to 0, delta is equal to 0. So if theta is equal to 0, the combination of these two is 0. The only unknown is m. To solve the problem, it just gives you ma is equal to wl squared over 8. And again, as soon as you plug that moment in our real structure, make a moment about a, the only unknown, this time rb is unknown on the structure, and you can easily go by counterclockwise wl squared times over 8 minus distributed load with the distance of L over 2 W negative W times L over 2 plus RB times length, which is R. Only unknown here is RB, and if you do so, it just gives you a same numeric value 3 over 8 W. Definitely A, RA is 5/8 of W. So this is what we are experiencing. So you can attempt your problem with, you can consider any part like redundant, but it's offered to go with the easier one. Thank you. We'll solve more problem in terminate structure force method.